Hello and welcome back. Welcome back to our series of events for students, online trainings, and so on. We will do our introduction to timber design today. My name is Jürgen Teilmann. I work with Dlubal software, mainly in customer support. One or two of you maybe have seen me before. And I will guide you through today's event and will host this session. By my side is my dear colleague Rebecca. Rebecca, will you please do me the favor and introduce yourself? Sorry, I'm afraid I can't hear you. Have you turned your mic on?
Oh, sorry. Yeah, so hello also from my side. My name is Rebecca and I work at Dlubal Software, also mainly in customer support. And today I'm answering your questions during the training.
Yes, thank you very much. So you heard her. If you have any questions during the training, don't be afraid to ask your questions. I will show you where. So I will now turn off my camera so you get the full screen experience. And I switch to the PowerPoint presentation. So we have our control panel of the GoToWebinar. If you can't see the panel, you know the drill. There's the orange arrow. You can hide or show the panel. You can also adjust your audio settings. And the main part for Rebecca will be your questions. You have a tab of questions and just enter the text and hit enter, and your answers will come in as quickly as possible. Okay, to the whole series of events, you've heard quite a lot until now for the use of RFEM 6. And today is my favorite part of this whole series, the introduction to timber design. So what are we going to learn today? I have brought 4 different examples. This is just a case of for you leaning back and watch. You don't necessarily have to model along. Maybe the first example you could model along, but you don't really have to. All the other 3 examples I use prefabricated templates, so it would be very, very hard for you to follow up if you would like to model along. But that's not a problem. You will get all our examples afterwards in a zip archive. Good, so that's our today's program. Just to let you know the 4 models we're going to do. We start with an introductory example for a timber column where we're gonna perform a stability analysis in timber design. Then I will give you an introduction to design supports and notches in timber design. And then I will model and design a Duopitch roof beam for you and a lattice truss. So that's the agenda for today. It will take about an hour, maybe 5 or 10 minutes longer, but I guess you'll have the time. And then before we start, I have a small question for you. And this is, have you already carried out a timber design using structural analysis software? Just for me to get a bit of a feeling how much experience you have in this topic. Okay, most of you have voted. I give you another 3, 2, 1, and we will close the poll. And I share the results. So most of you already have done timber design with structural analysis software. Not a problem for you who don't have, but it would be interesting to see if you will find big differences in RFEM compared to other software you maybe have used before. I think it's very intuitive to use RFEM for timber design, but you can see for yourself. So I hide the results of this and we jump right into RFEM. You already know this screen, and I will open a new model. And I will call this a timber column, timber column 1. I choose a project because I have already a project on my filing system. I make this a 3D model and jump to the add-ons where I activate the timber design. And after that, it's very important that we go to the standards and write the first one, the standard group for the load case classification. It's not only the EN 1990, it's vital that we choose the 1990/timber here with regards to the SLS. You will see later what this means now. We don't use a national annex today because this is an international event, so we're going to use international standards. Also, because the timber design is activated, we can choose the standard for the timber design down here. Okay, that's all I need for this model. I hit OK. And my model will be created in the according project. Good. I just delete all of these materials and all of these thicknesses. I don't need them for now. So we start with a blank page. And I just want to design one column. So I say one single member, and I can say perpendicular to the working plane. So I'm in the dialog for a new member. It will be a beam. I need a section. It will be a uniform distribution type. I'm starting with a new section. I'll make this one parametric massive. Make it a rectangular beam. I added the dimensions, make it 160 millimeters in width and 200 millimeters in height. So these are the dimensions for our cross section. I jump back to main because I haven't created a new material yet. So I jump to the library for my materials. I'm already in the section European Union and timber. And now I just utilize our search looking for C24. Make it this softwood. Good, that's what I wanted. So now the material is assigned. I can say OK. I have a section with material, say again, OK. And now you see my mouse cursor has already attached a visualization of this beam I want to create. You can see the dialog on the left. In this, I enter a length of 4 meters. And you see that at my mouse cursor, if I take this to the origin point of my coordinate system, the column will be pointing downwards. This is something I don't want. I want it pointing upwards. So I just use this button in the dialog to reverse the orientation, and I can simply set my column where I want it to be. I dismiss the function with a right click to the mouse. And well, that's basically all for this column. We of course need now some nodal supports. So I go to nodal supports, use this hinged one to the bottom node, say OK, hit apply to directly create a new one. This is just
Jürgen, we can't hear you anymore, and we also only see a frozen screen. So I hope that Jürgen will be back in a few seconds. So Jürgen, you are still not hearable and your screen is still frozen. Maybe you can switch it off and on again. Okay, now we see your updated screen, but we still don't hear you.
You don't hear me?
Oh, now we hear. I can hear you again.
Okay.
So maybe you could repeat the last like 5 minutes.
5 minutes. Okay, that's
Yeah,
quite a lot.
it was
Okay,
quite a
good.
lot.
I asked you. Yeah, I'm very sorry about this. We had some internet trouble. I'm glad my colleague in the office brought me up to this. So I just jump back a little bit. Okay, Rebecca, can you please help me? What was the last thing you heard from me so I can jump back to this moment?
I think the last thing was that you modeled the beam, and yeah,
So
so we
no
didn't
load
see the
case, no
loading.
nodal supports.
Yes, only the beam itself.
Okay, I will jump to the nodal supports. I will just delete them so you can see this again. I just need a hinged support on the bottom. It's like this. I guess you all know this. And I hit apply so I can stay within the dialog. There I created a new nodal support just to get a lateral fixation in the x-axis and around the x-axis. I say OK. I can assign this to the top node and say OK again. Whoops, this was wrong. So now I double click on the nodal support again. These errors can happen very often, but that's not a problem. You just double click on the support itself, and then you can choose from the list. And this is my nodal support number 6, the one I have just shown you. Okay, I go to the rendering just to check if this is the correct type of my nodal support. Good, now to our load cases. What I have done here, I have deactivated the self-weight because I want to apply a design load. That's why I called it design load. In the next phase, I deactivated the combination wizard. And yeah, this is something I have to tell you. This is important. This is the main reason why we choose the standard EN 1990 with the slash timber, because we have to choose our load duration. So in our terms, we're going to use a medium term. And if we haven't chosen the correct standard, this whole part wouldn't be available. So we wouldn't have been able to define a load duration. But now we are, since we have chosen the correct standard. Good. Now design situations, there are by standard some design situations predefined. So we have our ultimate limit state and several serviceability limit states. In this dialog, I just deleted our SLS design situations because I only want to perform a stability analysis, which is of course a ULS design check. Since I have deactivated the combination wizard, I had to create a new load combination using the button with the star right down here. And I have just assigned our design load ×1. So that's all for the load cases. And the nodal load is pretty easy. I go to the part where I have all my loads. I have the nodal load. I can, since I'm now in the load combination, I can now choose the load case where I want to apply this load. And within the dialog, I can also jump between. Well, it's pretty dull right now because I have only one load case defined. But yes, you can switch if you have several load cases. I assigned the load to our top node. Do this again. And then just entered the magnitude and the load direction. And that's how I got this 150 kilonewtons. Good, so that's for the load. And now I will jump right back into the member. And you can see that we have the design properties activated. And I'm going to jump to the design types. So since we are in Timber Design and it's pretty common to use the equivalent member method in Timber Design, I have created a new effective length. I'm going to edit this. I have neglected the lateral torsional buckling because I wouldn't expect any lateral torsional buckling in this massive rectangular section here. So I have just deactivated the lateral torsional buckling and jumped straight into the nodal supports for the effective length. We can switch to the dynamic rendering of our model. And now I can go to, when I click on a node, you can see a small arrow which shows us this is our node 1. And on the top node, which is node number 2, I will release in Y direction because this is exactly what our global supports do. Okay, I will leave the factors for the effective lengths at 1.0, and I say OK. Say OK again. And now, oops, I have forgotten something. Still in the design types, we also have our different service classes. So when I edit this, you will get, again, like in many dialogues in RFEM, you will get a small picture which shows you the different service classes, and you can choose between service class 1, 2, and 3. So this column is of service class 1. This is why I make no changes here. Good, I can start my calculation using this symbol, calculate timber design. Now I have an error. Let's see what I have done wrong. Yep. Something you might have seen by now, we have 6 degrees of freedom in our system. And I have a fully hinged nodal support at the bottom and no support in Y direction on the top. So you might have seen by now. I haven't so far, so it's good that the program tells me. I edit my bottom nodal support and of course need another fixation around the x-axis. Say OK, OK. So this is a pretty beginner's error I've made here, but you know, everyone can make such mistakes. So I calculate again. And now you see the design ratios on members. My stability check is fulfilled. I can make a double click on the results, so I can check the detailed results. That's pretty good. So everything's fine, right? Well, not exactly, because when I go to the design types and change the effective lengths, I go back to my dynamic rendering, and you see that in my global Y direction, this column is not. When I go to this setting, you can see the different Euler cases for buckling, and you can see that our column is like a cantilever. So I have edited our factor for the effective length wrong. I need this to be with a factor of 2. Okay. Calculate again. And now the design check is not fulfilled for the stability design of this column. So I've just made this to remind you that not every time the program says it's okay, it has to be okay, because there's always something you can enter wrong and the program, well, it doesn't know, it's just a computer. You're the engineers and you will have to consider the correct effective lengths for your members. Okay, another thing I want to show you in the input data of our timber design. You can go to our ultimate configurations. I open them, and when I go to our member stability, I can activate a stiffness reduction due to creep effects. So since this is only something we need in our German national annex to the Eurocode 5, you might not need this, but well, maybe if you study in Germany, you will need to know that if you want to consider creeping effects for service classes 2 and 3, here's how to activate this. Okie dokie. I save this file. And now I'm going to jump right into our next example. Just close this. And this is my example 2, design supports. Takes a few seconds to open. This is completely predefined. I'm not going to do any modeling in this example. I just show you some details for design. So what we have here is kind of a canopy from, well, made from timber. And we have one main girder carrying this canopy on the right side. And I have predefined some design supports. And just to give you an idea why we need these design supports, there's something they have two different main functions. The first is we need design supports as a definition of boundary conditions for the design of compression perpendicular to our grain direction. That's the first thing. And the second one is we need design support so we can perform the segmentation of members and sets of members for the deflection design. Okay, so I'm going to jump into our first design support. These are rendered with these pink things here. And our design support 1 is now considered with a length of 60 millimeters and the whole width of the member lying on top of it, in our case the girder. So the program calculates the area where the load is applied to. This thing is active, it's a direct support, and we have the effector for the compression set to 1.5. That's okay, that's a standard value, but you can also change this. And this is also active for fire design, but we're not going to perform fire design today. And it's also active for the deflection design. I hit OK, and just this time I'm going to use the table, which I'm much more comfortable when I'm using add-ons. I go to calculate, I say yes. And now we have the section proof, compression perpendicular to grain. This has exceeded the design check, so this is not fulfilled. So what am I going to do now? First of all, I double click on the results to get the detailed results. You can see this is our length of 60 millimeters, which goes into the calculation of the effective length of this design support, and therefore the effective area where our load gets distributed to. So what I'm going to do now is I want to spread the load over a wider area. This is why I'm going to edit the design support and just increase the length of it. Let's say this now has 80 millimeters of support length. That's all the changes I'm going to make. Say OK again. Yes, I want to delete the results and calculate once more. Okay, this is now something we don't need for the design supports. And you can see when I go to the member set, because the girder is a member set, I can see the design support compression perpendicular to grain is now fulfilled. I open the details again, and you can now see the changed length of 80 millimeters, and everything is fine right now. This is, I see the wrong set of members. Let's go to, where's the other one? Okay, so the girder is not a set of member, this is a single member, but you can also see that the design check is now fulfilled. Good, so what I want to do now with this model is I'm going to create some notches or openings. I will do some notches, openings are done in the same manner. So I'm going to our first member and edit it again. And you can see the design properties in this member are via the parent set of members. So I can do no design properties in the member, but I can directly switch to the set of members and edit the design types. And I'm going to need my local section reductions. Create a new one. And we have different types of reduction. So we can have a start notch, an inner notch, or an end notch. So since I want to do this notch at the beginning of the member, it's a start notch. And I'm going to add the dimensions. You can also look at the bitmap on the right to see what length do we need. It's measure number A. So this is going to be 4 centimeters. So in meters it will be 0.04. I'm gonna orient this to the depth of the beam with a reduction height of 100 millimeters, and notched from edge the plus axis. So in our example, the downside of the beam. It can also be the upside if you want to, but in our case, it's the downside. Also, this notch is at a support, so I just activate that it's a notch at support. Okay, yes, I delete my results, hit OK in every dialog, and calculate this thing once again. Good, I go to my design ratios on members again. Go to the member sets, and you can see the notch at support. It's here, section proof notch at support, and you can see the details of this design check. Okay, one thing I want to address is we have a small error, non-designable, because I have added this notch at the support. We are now not able to perform the compression perpendicular to grain in this point, but this is something our development is already on. It shouldn't bother us now. Later on, I'm sure this function will be ready to come. Good. I will save this, and then did it work? Okay, I say yes, save it. And while the program closes the file, I have a second question for you. So get ready. The question is very difficult. For the verification pressure perpendicular to grain direction, design supports must be defined. So is this true or false? So there's only one correct answer to this question. Good. Okay, while I give you a few seconds while my program opens the next template for the next model. Okay, it's open. I will close the question and show you the results. Wow, 100% correct answers. That's cool. I like that. Good. So before I start with the next example, once again, I want to apologize for the freeze before. And Rebecca, do you have any open questions for me I need to address?
No, there are no unanswered questions. You can continue.
Awesome. Okay, that's good. Thank you very much. Okay, as you have seen, I have a kind of empty template right here. I activate my grid. And you can see that I have a material defined. I have two different cross sections defined. And I also have several load cases. Good. This is just to save us some time. I'm going to start with a new member. So this is just a simple member. it's going to be a beam with a section with not a uniform type of section distribution. You might have seen this before. We can do some tapered beams and tapered at the start or in the beginning of the beam, and we're going to need a saddle distribution. So we can do this like shown on the right with such a fish belly shape, but we need the alignment on the bottom to have a distribution like this Duopitch roof. Okay, so alignment at the bottom. You can also adjust the location of our saddle point. I will make this at the middle at 50% of the length. You can also set an absolute number for this middle point. And I'm going to assign our cross sections right now. So you just go to the picture on the right, just to be sure. We have I, J, and K. So we have at the start, at point I, we need the first cross section. I choose my predefined cross section number 1. At the end, it will be the same as at the beginning. So I say S member start. And at the internal point, we need our second cross section. I just assign this. And the material is also assigned already. Okay, good. And now I'm going to start at the origin point of our coordinate system and make this beam 24. Yes, it's 24 meters long. Where was it? There it was. 23, 24. So this is our dual pitch roof. You can also see I have the name of our cross sections visible. I go to the display navigator, to members, and then you can show or hide different additional informations to your beam if you want to have them. I just deactivate this. And what I'm going to now is I divide this beam because I want some internal nodes for a lateral fixation. Okay, so how do I get these internal nodes? I just right click on the beam. I say member, divide member with n intermediate nodes. And I'm going to divide it by with 5 nodes. And what I want to do is I don't really want to divide this member. I just want set internal nodes on it. So I say create on member nodes without dividing the member. And I say, okay, we'll see what that means. I just have these blue nodes instead of the red ones, which come by standard. And this is still one member, but I have now my 5 internal nodes on this member. Okay, so I will edit the member for my design properties. I go to the design types again. Like before, I will add some effective lengths. Now for this cross section, it would be good to consider the lateral torsional buckling. And we have 3 different methods of determination of the elastic critical moment. So I will use the analytical one here in this example and go to the nodal supports to get our lateral supports on the intermediate nodes. So I will use the button, select member, and select the one member I have, and automatically I get all our internal nodes displayed in this dialog. And I just add a lateral support for all of these, and you can see our different effective lengths around the y-axis. We only have one length, like in the dynamic model, it's from node 1 to 2, and around z-axis we have all our different lateral supports considered for calculating the effective length. It's also possible for our supports to consider an eccentricity, like upper flange, lower flange, if you want to, but I will not use this in this model, just to show you that it's possible. Okay, this is the effective length now for this. We have our service class 2. Okay, let's use this. And now I need some load on this thing. I go to my load cases. At first I check the German Eigengewicht, which is self weight, of course, in English, that the self weight is deactivated. I hit on apply, and I go to my, just call it in post loads, and snow. Good, say okay. And then I add the loads for self weight. Because I have deactivated the self weight, I want to add it manually. Since we have a member, I'm going to use the member load. And it's pretty much the same as in our nodal load. I have a load case. I assign the load to an object. So I go to member number 1. I enter the magnitude, 1.02 kilonewtons per meter. Make this force uniform in the global z direction on the true length. I hit apply and next. So this load is now, you can see it, is now applied in our load case 1. I'm still in the dialog, switching to load case 2. Assign a new load to member number 1. So this is pretty much straightforward. 2.7 kilonewtons per meter. Again, a uniform force in the global z direction. Apply and next, and at last the snow load, again to member number 1, now with a different magnitude, 3.15 kilonewtons per meter. And here's the thing, that we have global and z on projected length for the snow load. I hit on OK, so you see the load for the snow and for our other load cases. Good, so since I want to calculate this thing now, you might know that we still need some supports because elsewhere it would fly around. So I just add nodal supports again. This time I use the roller. It's this one, roller in X direction. To the right node. And the hinged one. Sorry, I first have to apply it. And I use the hinged one on the left. Hit OK. And this looks pretty good. So I just say I will calculate all. So now I have a small mistake. You can see that coordinates of node number 3 and 6 are too close. I go to the table and you can see I have two identical nodes. What happened here? The first thing, the middle node, we have created a intermediate node by the distribution of our cross section. So our middle node at point K is defined with a internal node. And also, since I have divided the member by 5 internal nodes, there's also another internal node at the same position. So the easy fix for this would be to just delete one of these doubled nodes and everything should be fine. Good, so I'm looking at these results. You can see in the result navigator that the normal forces of this member are active, and you can also see that we get compression. So you might wonder why we have compression, because we only have bending on this beam, but this is something hand calculation does not consider. The hand calculation completely neglects the statical line eccentric to the geometric line. So this normal force is something that only comes in reality and not in your hand calculation, but it's here, it's active, and it has to be considered in design. So this is absolutely correct with this normal force for this section distribution. Also, the moment distribution in this case is due to our eccentricity of the static line. You can see that this is not a perfect parabolic graph here. And the location of the maximum bending stress is not in the middle of the beam, what you would have expected if we had a constant cross-section distribution here. This now leads me to one thing that you might already know, but you really have to consider this when you're calculating and designing a structure like this, is that we also have, I go to calculate and the mesh settings, we also have an FE mesh on members. So this is represented by the number of divisions for the members. And now we have 24 divisions. I just set this to a very small number, to a ridiculously small number. I say OK and calculate again. And now you see this diagram for the bending. This is not usable anymore. So the ones of you who have already heard our training in the introduction to FEA, who know what comes next, it's the basic to set every FE mesh, even on members, to be as coarse as possible, but still as fine as necessary. And this is a case where we need a finer mesh just to determine our place of the maximum bending stress in this member. Good. So to our timber design, we now have our section proof and stability proof for this member. I go to the section proof, and here's something I want to show you. It's the cut to grain angle. You might need this for your studies, for some exams you need to perform. You can get that angle here. Good. And that's all for this model. Again, I will save it and jump to our third question I'm going to ask you. This again is something you should know, should have heard by now a lot of times. And to determine the location of the maximum bending stress, a not too coarse member subdivision should be chosen. So this is about the FE mesh refinement on your members. Okay, most of you, well, a lot of you have voted. I will close the vote in 3, 2, 1 now. And I will show you the results. Wow, I'm really impressed with you. That's correct. So this is all to the sentence, you should choose your FE mesh as fine as necessary while as coarse as possible. And in our case, it would be too coarse if we didn't see the location of the bending of the max bending stress. So this is true. Good. We will jump to our last example for today, where we had the poll open. I opened another template. Again, it's the same as before. I have prefabricated a few materials and cross sections just to save time. Okay, there's one main thing I want to show you in this example, and this is why I go back to the model base data here and to the settings and options, because we have in this model activated member representatives. Good. Just to get you an idea of what member representatives are, they help you modeling and designing in a very quick manner because they are kind of templates. So you use all members with the same material, section, line type, member type, and length, and you can also define different other member properties for this template you want to use on a certain on a certain member representative, and they will help you make it very easy to select multiple members at a time, even in a rather complex model. Okay, so I'm going to start right ahead with my member number 1. It will be the upper girder of our truss. So I will just make a simple member again. This would be a beam. It would be a uniform distribution with our section number 1 with material number, material number 2. And I say, okay, and this will again be 24 meters. Oops. For our upper girder. So this is now a straight member. I want to divide it. with one intermediate node, and this time really divided to have two members afterwards. Okay, and this middle node is going to be moved up. Not a copy, really moving it in the global Z direction by -1 point, oops, what have I done here? 1.8 meters. So it's up here. And you may already see that we not only have our red nodes, which have a round shape, we also have these small red squares. And they are the visualization of our member representatives. So we have member representative 1. I click on it and both our members of the upper girder are selected now. Okay, good. So next I want to create the lower girder. So I go to new member once again. Again, a beam. This time it will be section number 2. Again, material number 2. And I say okay, and this is just to close this thing. Boink. Good. So I want to use kind of a 3-hinge train in this model. So I need a hinge on the top node of the whole truss. So I just take the left part of the upper girder. I activate my hinges, go to the tab hinges, and at the end of the member, I create a new. Well, it was already predefined, so I create it once again. It's okay, I just need a member hinge, a moment hinge. So we have our hinge on the left. You could ask, why didn't I also make a hinge on the right part of the upper girder, but that would make a so-called hinge chain, and this middle node would become unstable. So I have already considered this and only made a hinge on the left side of the upper girder. Good, now I will divide all 3 of my members again. So I have 3 members selected. I divide them with 2 internal nodes. And this time again, it will be divided by these members, nodes of the type on member. I always say this wrong. Good. Now I fill up all the internals with our truss members. So I create new member, choose the type truss. You can also see on the right in the bitmap that these are like beam members, but they have internal moment hinges assigned to them. Good, I go to section. This one will be section number 3 with material number 1, a squared section. Say okay, and just quickly doop, 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 doop. And right click to dismiss this. Good. So this looks pretty good. We still need some global supports. So it's the same as we have done several times today. This is now in German, should be hinged here. So you can learn a bit of German again. To the left, the gelenkig means hinged, and verschieblich in X means a roller in X direction. And put this to the right. And we have our supports. Good. Now I want to go through my prefabricated load cases once again. This time we will consider the self-weight of this structure. In load case number 2, I will again assign some member loads, this time on the upper girder. So it's member 1 and 2 with a magnitude of 3 kilonewtons per meter, global Z direction on true length. Good. And load case number 3, new member load. This time 3.5 kilonewtons per meter, global Z direction on projected length. I say OK, and then we control snow load on projected length, other load on true length. Good, I just switch to my load cases again and to the design situation. And you can see that in the design situation is where you actually choose your combination wizard to see after which calculation theory the load combinations are built. So this combination wizard is set to geometrically linear. It can also be set to the pi delta if you want to, but in our example, we're gonna use the geometrical linear method. Okay, that's for the load. And next, I wanna edit our design properties. And now our member representatives come into place. When I go to member representative number 1, my members of the upper girder are selected. I just double click on one of these members. They are all selected now. So now all my members of the upper girder are selected and can be edited simultaneously. I'm sorry for my pronunciation here. I go to the design types. I will add an effective length, or should I say I will choose one I have already predefined. I go to edit just to show you what is done here. This is again, analytical method for lateral torsional buckling, nodal supports, and we have our effective lengths. Now you can, in the previous example, we had our effective lengths calculated by the nodal supports, but you can also override them manually. And in this case, with absolute values. When I uncheck the box, it's with a factor. When I check it again, it's with an absolute value, in this case of 7 meters, or in Z direction, 2.58 meters. Okay. Okay, I go to the lower girder. I could use the member representative once again, but there's no fun in this because now we only have one beam with this representative. Go to the design types and add effective length number 2, also predefined. I show you what I have done here. So this is with no lateral torsional buckling and just a factor of 1 for the effective length. Good. Okay. And for all the others, I can go to my data navigator And I can also pick all member representatives directly from the navigator. So if you know that these are the Truss members, you can select them all and edit them all simultaneously, all at once. Go to the design types, effective length number 2, same as the lower girder, and say OK. Now when I calculate all, we can see our results on this lattice truss. So we're now in the global deformations. I just jumped to the timber design. There are now many section proofs not fulfilled, but in the end, this will be your job as upcoming civil engineers to see what went wrong here and what measures have to be taken to get this done properly. Okay, last question from me for today. That was the main aim of our last example, is just what are member representatives? What do you think is correct from these answers? Okay, I will close the question in 3, 2, 1. And I will show you the results. And yeah, there was a bit of a trap I set up here because in this question there could have been more than one answers for you to choose, but there was only one answer right, and that is of course the upper one, which 90% of you answered correctly. So I'm very impressed with you. Thank you very much for your attention here. And yes, just to address the second answer here, members grouped together like one single member, that would be using a set of members, not a member representative. So that was a bit of a trap, I admit it, but at least you have made a good result here. Okay, Rebecca, are there open questions I need to address?
No, there are no open questions left.
Awesome. Okay, so before we leave today, I will just skip to our website, dlubal.com. And if you have any questions up your mind that will come later, you can also go to, I just switch to the English page. When you go to education, you have RFEM 6 for students, so you can always rewatch this video if you want to. And you will also get a link to this video if you want to. Good. Otherwise, you can look at our company and the support and learning. If you have questions, we have our FAQ section, our knowledge base. If you have any questions when working with our software, we'll be here for you. We won't let you hanging down. Okay, that's all for our training today. Thank you very, very much. It has been a pleasure. So maybe we will hear from each other. And one last thing I would like to ask you is to stay here in this training for just maybe 5 minutes when I close it, because there will be an evaluation for me as a presenter and for the whole training as a whole. And in this, you will get to rate me and my colleagues. And if you say, hey, that's a good guy, I want to see again, please give me a 5-point rating. And if you say, this guy is very, very poor, I don't want to see him again, so you can also give me a 1-point rating. That's up to you. Just be honest, and we're fine with that. Okay, once again, thank you very much. It has been a pleasure, and also I'm really impressed with your attention. Okay, goodbye, and maybe we will see each other.